Okay, so the plan for today is to just finish up the ratio test and to start power series. Um, so power series may be the kind of last major topic that we'll discuss in Calc 2, right at the end of chapter 11. Super, I think, interesting and valuable topic that if you haven't seen it already, things like power series, Taylor series, Maclaurin series, um, in your other courses, I think you will, you'll see it. Um, Comes up in things like physics and engineering and the applied uh, hard sciences, really all over the place. So, um, and it's entirely possible that if that you've even seen it and just haven't known what it was called, or they said, we'll just throw away the higher order terms. Well, that's basically using a power series or a Taylor series. Um, yeah, so that'll wrap up chapter 11. And then we have this little, I don't know, like little bit of chapter 12 that we cover in Calc 2. So what kind of happened was Calc 3 was expanded just because of the demands of engineering programs and so on to include vector calculus. But that kind of pushed a little bit of the Calc 3 material into Calc 2 and a little bit of the Calc 2 material into Calc 1. So in Calc 1, we start into some things like substitution rule and some integration techniques. And in Calc 2, we cover a little bit of 3D geometry kind of in preparation for Calc 3. So the lines have become blurred a little bit. But that's really the plan for the rest of the course. Wrap up chapter 11 and move into a little bit of chapter 12. The quote of the day today, there's a few quotes. We cancel Tuesday's class, so this is the Tuesday quote: "The compound interest is the most powerful force in the universe, that self-reinforcing phenomena, positive feedback systems um, can, can be very positive. Like people say, invest when you're young and you have time on your side, and that's hugely advantageous. Or they can be very disastrous, like the Tacoma Narrows Bridge, if you've ever seen that. Um, if you've ever seen that video where the bridge was like bouncing up and down and quite literally tore itself apart. Um, so from an engineering standpoint, a lot of times you want to avoid positive feedback, but sometimes you can take advantage of positive feedback. So things like amplifiers and so on. But the other quotes of the day for today are from chess grandmaster Marius Ashley, a US grandmaster. There are three types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, it's foolish. And then the Warren Buffett quote: there are no called strikes on Wall Street. And I think the ideas behind these quotes, the common elements behind these two, are something like when you're going to make an important life-changing decision. So for instance, making a trading, say, my bishop for your knight, will be a fundamental change to the game that can't be undone. If I move my bishop to this square, I can move my bishop back. I can undo that if I don't like that move. But if I trade a piece, that's more consequential. Um, or somebody like Warren Buffett entering into a big trade, that's a pretty consequential decision to make. So when a consequential decision is going to be made, make it with a lot of care, whether it's in chess or finance or just generally in life. The higher the consequences, and the more permanent the decision is, the more care should be taken to make that with a really high level of fidelity. Okay, so jumping into absolute convergence in the ratio test, really quickly recall a couple of ideas from last time. So definitions, we say that a series is absolutely convergent if, when we replace the terms by their absolute values, it still converges. We say that a series is conditionally convergent if the series itself converges, but the series consisting of the absolute values diverges. So of course, for any positive series, for any series whose terms are all positive, or for that matter, for any series whose terms are all negative, or any series that is a positive series or a negative series after a certain point in the series, so for all terms from this point on, uh, then absolute convergence is the same as regular convergence. Or another way to look at it is a necessary condition to have a conditionally convergent series is that you have to have infinitely many positive terms and infinitely many negative terms. Another way to say that. And that idea will come up at the end of this section with a really interesting little theorem. We also developed I shouldn't say developed, we gave a motivating argument for the ratio test and stated the ratio test. And particularly, we're looking at the limit of the absolute value of the next term to the current term, limit of the absolute value of the ratio of the next term to the current term, as n goes to infinity. And if that limit is L, a real number for infinity, then we can say the following: if L is less than 1, then the series converges absolutely. Of course, this is an absolute value, so L is always going to be, if it exists, greater than or equal to 0. But if it's less than 1, the series converges absolutely. If it's strictly bigger than 1, the series diverges. And if it equals 1, the test is indeterminate. We have to do something else to figure out convergence or divergence. Okay, so let's take a look at a series that has its terms defined recursively. We saw this kind of idea of recursive definition back all the way in sequences. But let's think about this series where a1 equals 1, and then an plus 1 equals 1 plus 1 over n to the n times an for, I guess, for n equals 1 or larger. So for instance, a2 would be 1 plus 1 over 1 to the 1, or it would be 2 times a1. And a3 would be 1 plus a third cubed times a2, and so on. I want to compute each of those terms and then add them all together. And my question is, does the series converge or diverge? Well, let's check with the ratio test. So what is absolute value of an plus 1 over an? Well, I see that I can just divide this over. That's absolute value of 1 plus 1 over n to the n. We don't really need absolute values there. I can get rid of those. Oh, got rid of my n there as well, or part of my n or something. And the question is, what happens to this as n goes to infinity? And we actually might recognize this this limit here. This goes to the number e, or about 2.718. So the ratio of the next term to the current term does go to a real number, e, and in this case, a real number bigger than 1. Therefore, this series diverges as demonstrated by the ratio test. Okay, let's look at an example of a series that we've seen before. We already analyzed the series, and we know the alternating harmonic series does converge. But we know if we took the absolute value of each term, we would just get the harmonic series, the regular harmonic series, which diverges. So we know that this cannot converge absolutely, but must converge conditionally, because the series converges, but the series consisting of the absolute values of the terms diverges. What does the ratio test say about this series? So let's look at the absolute value of an plus 1 over an, or that's the absolute value of negative 1 to the n plus 2 times 1 over n plus 1. That's an plus 1. So replacing all the n's with n plus 1's, and then divided by an, which is negative 1 to the n plus 1. These are all under the absolute value, times 1 over n. Of course, the absolute values just get rid of the negative 1 business in front. And we get n over n plus 1. And what happens to this as n goes to infinity? as we would expect, this goes to 1. So the ratio test is indeterminate. The ratio test does not make a claim whether it converges, diverges, converges absolutely. It doesn't make any claim at all. It says you have to do something else to evaluate the convergence properties of this series. And we already have done other work showing that the alternating harmonic series does converge as is, and that the harmonic series, the series consisting of the absolute values of the terms, diverges. So we know that it's convergent conditionally from a combination of previous work and the ratio test coming back indeterminate. When the ratio test, maybe I should say inconclusive, indeterminate means something slightly different in some mathematical contexts, but we see that when the ratio test reaches a firm conclusion, the only options are absolute convergence or divergence. The ratio test can't come up with a conclusion that says, just by the ratio test, this series converges conditionally. That's not something the ratio test is set up to do. Okay, and then to wrap up this section, we have a theorem, and it's probably one of the strangest theorems in mathematics. Uh, I don't know, there's a lot of strange theorems in mathematics, but it's definitely a contender for, say, being in the top 5 or maybe top 10. Okay, so let's see, what does this theorem say like more precisely, and then what is it saying roughly speaking? I'm not going to spend much time on this because we have a lot to get through today, but here's the theorem. Given S and R, given some real number, pick a real number that you like. It could be 100, it could be pi, it could be negative 1,000, whatever real number you like. And given a series that's conditionally convergent. Maybe you pick the alternating harmonic series, maybe you pick some other series, like an alternating P series kind of deal or something like that, or maybe something else that's conditionally convergent. Now, in the back of our minds, we think conditionally convergent, that means it has to have infinitely many positive terms and infinitely many negative terms. And the claim is, then there exists a permutation of the sequence AN, call it sequence BN. Permutation meaning we have a one-to-one correspondence between the terms. So maybe A1 turns out to be B10, and A2 turns out to be B7, and A3 turns out to be B100. But the list of A's and the list of B's, there's a one-to-one relationship between them. So there's a permutation of AN, call it BN, such that sum BN equals S. So what is this saying? It means in a conditionally convergent series, changing the order of summation of the terms changes its sum. And I mean, if we just change, like, if we swap the first two terms around or something, that doesn't really do it. We have to change the order of the terms kind of, infinitely far out, all the way out through the entire tail. And not just that, not just that if I change the order of summation, it changes its sum, but actually any sum can be achieved with a proper rearrangement. This is pretty striking for a couple reasons. One, it really breaks with our idea of how sums work. When we think of even very large sums, even if I was to add together 100 billion different numbers, okay, when I add the first 10 together, if it's in a different order, I might get a different sum. But when I add the whole thing together, I should get the same sum. But when I have an infinite series like this, or just a series, calling it an infinite series is a bit redundant, um, but when I have a series or an infinite series like this, some of those kind of gut feeling, ideas kind of go out the window, right? We have to be very careful when we're talking about really anything to do with infinity. And not just that it changes its sum, but that we can actually achieve any real number sum we want. So by making the permutation the right way, if you want your series to converge to pi, you can rearrange, say, the alternating harmonic series to make it converge to pi. Or if somebody else wants it to converge to, negative e, they could find another rearrangement that converges to negative e. And really we're certainly not going to go through a proof of this, and you could barely even call this a sketch of a proof, but I'll give you kind of a bit of an idea to maybe make this seem a little bit less paradoxical and a little bit less strange, although it's still quite strange. If I consider the sum of the ANs, or I consider the terms just as the sequence AN, all right, for it to be conditionally convergent, there have to be infinitely many positive terms and infinitely many negative terms. So I can split this into like sequence AN plus and sequence AN minus. So this is just the list of the original terms in their same order that are the positive terms, and then splitting off the negative terms into this other list of the infinitely many terms in their original order that are the negative terms. These are both infinitely long. If either one were finitely long, then far enough out into the tail, you'd have essentially a positive series, say, and then you can't have conditional convergence because then absolute convergence is the same as regular convergence. Or if they were all negative after a certain point, same thing could be said. So these are infinitely long. These infinitely long list here and infinitely long list there. And furthermore, this sum, the sum of just the positive terms, not the absolute values of all of the original terms, but if I just pluck out just the positive terms and skip over the negative terms. I'm being fairly imprecise here and hand wavy, but like I said, this isn't crucial for the course material. It's just a cool result. So I want to present it, but we're not being really careful about it. This sum has to be plus infinity. And this sum, the sum of these negative terms, just forgetting about the positive terms, just add up the negative terms, has to be negative infinity. And this is, I think, the real key idea here. The real crucial idea is that neither of these sums converge to a real number. If they did, let's say that, this sum was negative 10 instead of negative infinity. Well, then, like, wouldn't the sum of all of these, because remember, this sum is a real number. It converges, right? It's conditionally convergent. So the sum of all of the terms plus and minus converges to a real number. But if the positives added up to infinity and the negatives added up to just, say, negative 10, well, then the sum of all of them would have to be positive infinity. Yeah, we didn't prove that carefully, but I think that is plausible. But that's kind of the crux of the idea, is that the sum of the positive terms has to be infinity, or the series consisting of only the positive terms has to diverge to infinity, and the series consisting of only the negative terms has to diverge to minus infinity. So their partial sums have to be getting larger and larger and larger positive, and then larger and larger and larger negative. And what do? Well, I start adding, A1 plus, A2 plus, A3 plus, and so on. Let's say that I'm looking to get pi, for instance. I keep this up until, at whatever S, I'll just call it S superscript 1, this first partial sum that I'm interested in of adding up a bunch of the first positive terms is bigger than pi. I know I can do this because if I keep adding positive terms together, I shoot off to positive infinity. So I can eventually get above pi. And then I switch. As soon as I get above pi, I switch and start adding the negatives. Maybe I have to add 10 of the negative ones together. to get, say, S2, which is the partial sum up to where I am so far, to where we're below pi again. Again, I know that I can do this because after, say, A3 plus, my partial sum was maybe the number 5 the first time I got above pi. And then I start adding negative numbers. If I keep adding them forever, I'll head towards negative, I'll get to negative infinity in a sense. So I can certainly get below pi. And I just keep this process going. As soon as I get below pi, I start adding positives again until I get above pi. As soon as I get above pi, I add negatives again until I get below pi, and so on. So we can see how we're not going to, how we can always get back above pi and can always get back below pi. The question is, well, why should we converge? Why should we converge to pi? And kind of the answer is that, well, because this series converges, again, this is pretty hand wavy, because the original series converges, we must be getting small fast. The terms of the original series have to be getting small fast as I head into the tail, which means that because these elements consist of selections from the original series, they have to also be getting small fast. Okay. So that's why I have to uh, converge. I mean, again, this is far, far from anything that would resemble a mathematical proof and is barely even a sketch of a proof, but I'm trying to just hit the kind of high points here and resolve the paradox a little bit. But this is just kind of another warning that when we're dealing with series, even with convergent series, right? I mean, this sum an is conditionally convergent. It's a convergent series. You might think, oh, it converges. It works very nicely. It has nice properties. Not really. This is kind of a very wonky property that if we just swap the terms, you know, and if we make infinitely many swaps, if we change the ordering infinitely far out into the series, then we come up with a different summation. And in fact, we can construct any a summation or a permutation that results in a sum that's any real number that we want. Okay, so here are some actual properties. These properties are true, and they'll be very useful. So some helpful properties. If the series an and bn converge, then we can say the following. For a convergent series, if we have a constant inside the series, a constant multiple, it can come outside of the series. And if we have a series consisting of the sum of two terms for each of its terms, so I have like for the first term of the series is like a1 plus b1, and the second term is a2 plus b2, and so on. I can split those apart into the individual series if some an and some bn both individually converge. Be a little bit careful. It's not true to say the following, that if the series consisting of an plus bn as the terms converges, then the individual series converge and you can split the sum apart. That's not what we're saying. It's very important. The assumption that's being made here is the series individually converge, then we can split the sum apart. It's not if the series consisting of the sum converges, then we can split it apart. We saw an example with like, you know, sum 0 is sum 1 plus -1. Well, that's clearly not sum of 1 plus sum of -1. This converges to 0. This is like infinity minus infinity. It's indeterminate. So be really careful that the precise details matter quite a bit here. And another one is if I have a series sum an that converges and another series sum bn that diverges, then the series whose terms are made up of the sums of those individual terms must diverge. Okay. the contrapositive is, of course, true that if the series made up of the sums of the individual terms converges, if it does not diverge, then we cannot have one of them converging and the other one diverging. They either both must diverge, like here, or both must converge, like here. And in fact, we kind of saw that up here, right? Something, it's not exactly the same property, but something that feels qualitatively similar, that if I break a conditionally convergent series up into its positive bits and negative bits, both of those diverge. I couldn't have like one of them converging and the other one diverging. It's not exactly the same, but it feels qualitatively similar. Okay, so let's move on to power series. So what is a power series? Well, essentially a power series is an infinitely long polynomial. I could have a linear, quadratic, cubic, quartic, or I could keep going. So a power series is a series of the form sum n equals 0 to infinity, cn x to the n. We take x to the 0 to be 1, so we would write this as c naught plus c1x plus c2x squared, and so on. We could also consider a little more generally a power series sum n equals 0 to infinity of cn times x minus a to the n. So just shifting the center, so to speak, of the series to the right by a units, swapping x minus a for x. And we call this a power series centered at a. Or conversely, we could define this to be a power series, and this would be power series centered at 0. Both of these ideas will be quite important. Something that we might not initially appreciate, but this sum, and for that matter, all of its partial sums and all of that, these are actually functions of x, right? So this sum, this infinitely long sum, this series, if I put in x equals a half, I get one answer out for the sum of the series. If I put in x equals 2, I get another answer out for the sum of the series. Or maybe some values of x I put in, I get a valid sum of the series that's a number, and some x's I put in, the series fails to converge. By choosing the value of x differently, I can change the sum of the series or even change whether it converges or diverges. So this sum really represents a function that for certain inputs x, I get different outputs, either maybe a different value for the sum or maybe essentially nonsense, a series that diverges. And the sum is a function, let's call it f of x. The domain of that function is the set of all x for which the series converges, for which I get a sum that's a real number. So I can map real number inputs to real number outputs. If I try to put in a real number and the series diverges, that's just not allowed. We're not allowed to plug that in. That's not in the domain of the function. So for example, the power series sum n equals 0 to infinity x to the n, we I suppose cheated a little bit already because we looked at sum n equals 0 to infinity r to the n, and we asked for what values of r does that converge. Well, that's pretty darn close to just asking a question about a power series, right? This is a geometric series. Sum n equals 0 to infinity x to the power n. And we know that this series converges so long as we are strictly between -1 and 1, so long as absolute x is strictly less than 1. So it's a power series with domain open -1 to 1. And this is by previous work dealing with geometric series all the way back in section 2. We have a theorem here. At first, it'll kind of seem like this theorem is just not saying anything at all, but on closer inspection, I think we'll actually see that there's something really interesting going on here. So theorem. given a power series, let's say a power series centered at A, sum n equals 0 to infinity, Cn times x minus a to the n, exactly one of the following three statements is true. Let me give even extra space here to make it a little easier to read. Exactly one of these following three statements is true. One, the series converges only at x equals a. The domain is the singleton, just the number a. That's the only number that can be plugged in. There's a little aside here. Remember, we can think of this as like C naught plus C1 x minus a to the first plus C2 x minus a to the second, and so on. If I think of my partial sums, they look like C naught plus C1 x minus a, C naught plus C1 x minus a, C2 x minus a squared, and so on. Clearly, this series always converges at x equals a. If I plug in x equals a, this term is 0, this term is 0, as is every term from there on out. My partial sums are all just exactly C naught. My first partial sum is C naught, second is C naught, third is C naught, and so on. So I always converge when x equals a. I always converge at the center of my power series. But it is possible that that's the only place that I converge. The second possibility that could be true is the series converges for all values of x, for all real inputs. The domain is the whole real line. That's a possibility as well. That any real number that I pick and plug in there, the series is going to converge and I'll be able to get a sensible sum out of it. Or three, this is the one that seems like it's just a catch-all for every other possibility, but on closer inspection, maybe not. Three, there exists r greater than 0, there exists a number r called the radius of convergence, such that the series converges for absolute x minus a less than r and diverges for absolute x minus a bigger than r, and may or may not converge the endpoints. So at first glance, it looks like statement 3 basically just says there's some interval that's bigger than just the number, they're just a single number, but not as big as the whole real line. And the series converges on that interval. It's like, okay, well, that doesn't seem to really say that much. But note, really what this says is it's not just some interval, it's actually a symmetric interval about the center of the series. So in short, power series converge on symmetric intervals about the center. It might include it might converge on an interval that only includes the center itself and nothing else. It might converge on essentially an infinitely wide interval around the center on the whole real line, or it might converge like if the center of the power series is at 2, it might converge on like 1 to 3 or on 0 to 4. But if the center is 2, it can never converge on like -10 to +3. That's not a symmetric interval. And by that I mean it can't converge strictly on -10 to +3 and nowhere else, because it's not a symmetric interval. So power series converge on symmetric intervals about their center. This has some really interesting ramifications that, like, if I rewrite a function in terms of its power series equivalent, the function might, converge on all the real line except for one point, but the power series cannot converge on the whole real line except for one point. That would not be a symmetric interval around its center. You can't just pluck out one point and say it doesn't converge there. It can only converge on a symmetric interval around its center. So it's going to have a lot of space, in a sense, where it's not going to converge, where it's not going to do a good job of representing the function that we might intend for it to represent. So there are interesting ramifications of this. And it is an important note that that statement 3 up here, where we have a radius of convergence that's bigger than 0 and less than infinity, this interval of convergence, as we call it, may or may not include the endpoints. So another thing that we'll see is we often do maybe a ratio test to kind of, let's say something like rough in the interval to basically get the radius of convergence. And then we have to check the endpoints of the interval of convergence specifically. We have to plug in this number, we get a specific series, and maybe we make an argument with the alternating series theorem to say whether it converges or not. And then we plug in this number and we make an argument using a comparison test to argue whether it converges there or not. So often we use a ratio test to establish essentially the width of the interval, and then we check the endpoints specifically using some of our previous tools and techniques. Unless, of course, the radius converges infinity, and then we don't have any endpoints to check. That's always a nice situation to be in. Okay, let's take a look at this example here. Consider sum n equals 1 to infinity, x to the n over n to the p. Find the radius of convergence and the interval of convergence. Okay, so I mentioned before that we often use the ratio test to find this radius here. I noticed that the center is at 0. And I'm looking for this to converge for, say, absolute x less than some number. Absolute x minus 0 less than some number. Or perhaps I end up in one of these special cases. So let me apply the ratio test here. What does the ratio of an plus 1 to an look like? So that is x to the n plus 1 over n plus 1 to the p times n to the p over x to the n. Well, something that always happens with my power series, the next term always picks up exactly one more factor of the variable bit. So when I take the ratio, I'm always left with just one factor of the variable bit. Right? X to the n plus 1 over x to the n just gives me x. And then I have some other stuff, n to the p over n plus 1 to the p. Now this x could be a positive number or it could be a negative number. I better keep it inside the absolute value. So the stuff with the variable x, I better keep inside the absolute value. But I see the n stuff. Here the n is always positive. N to the p over n plus 1 to the p. Now my ratio test asks the question as n goes to infinity, as the index of my term goes to infinity, what happens? Very importantly, x is not going to infinity here. The x is a fixed but arbitrary number. The ratio test is asking about what happens when we get further into the tail, right? X is fixed, but we are going further out that direction to the squared or the cubic or the quartic term. So as n goes to infinity, what happens? Well, this bit just goes to 1. So that's absolute x. That absolute x doesn't have any n's involved in it. It's just a constant in terms of n. It just comes along for the ride. It's just absolute x times 1 is what we go to. And my ratio test says that we converge absolutely if absolute x is less than 1. We diverge if absolute x is bigger than 1. And we're not really sure what happens if absolute x equals 1, if x equals plus or minus 1. What have I figured out so far? I converge absolutely, as I said over here is now off screen, but I converge absolutely for x less than 1. So I know that I converge absolutely on open minus 1 to 1. I know I diverge. When is that? When absolute x bigger than 1. That's negative infinity to negative 1 open, union, positive 1 to positive infinity open. I don't know what happens when x equals negative 1 or when x equals positive 1. I have to investigate those separately. These are the borderlines where my ratio test yields a 1 as a result and is inconclusive, so I have to check those some other way. But the ratio test helped me with, all of the infinitely many points on the real line. I just have to check 2 of them specifically now. So the ratio test came in pretty handy, but we do have to wrap things up a little bit here. Okay, so for x equals negative 1, what does my series look like? Well, that's sum n equals 1 to infinity, negative 1 to the n over n to the p, right? Well, what do I know here? I know this is an alternating series. If I look at 1 over n to the p, does it go to 0? Is it decreasing, or I suppose non-increasing? Well, I guess that's true as long as I have some n material left on the bottom. That's true as long as p bigger than 0. So I converge at x equals negative 1 if p bigger than 0. And what about x equals positive 1? Well, that's sum n equals 1 to infinity of, well, just 1 to the n is just 1. So that's 1 over n to the p. Hey, that's a p series. And this converges if p is bigger than 1. So for x equals positive 1, converges at x equals positive 1 if p is bigger than 1. So we converge on open negative 1 to 1 regardless uh, of the value of p. We converge at negative 1 if p is bigger than 0. We converge at positive 1 if p is bigger than 1. And we diverge on negative infinity to negative 1 or 1 to infinity, again, regardless of the value of p. So and just to be clear about the nomenclature here, my radius of convergence is 1. That's my capital R from above. And my interval of convergence is either -1 to 1 or -1 to 1 or -1 to 1, depending on the value of p. So this would be p bigger than 1. This would be p bigger than 0, but not bigger than 1. And this would be p less than or equal to 0. Less than or equal to 0. So I have 3 different intervals of convergence depending on the value of p. All right, let's look at this one. Sum n equals 1 to infinity of x to the 2n over 2n factorial. Find the radius of convergence and interval of convergence like before. So again, I'm going to take a look at an plus 1 over an in absolute value. So the n plus first term is going to be x to the 2n plus 2 over 2n plus 2 factorial. The n gets the 1 added to it, so that filters through to a 2 once the distributive property is done. We get a 2n factorial over x to the 2n for 1 over a to the n. This leaves me with 2 factors of x. So I have absolute value of x squared times 2n factorial over 2n plus 2 factorial. This is absolute x squared, and just put it all in one line. X squared over, and the denominator is 2n plus 2 times 2n plus 1 times 2n factorial, which divides out the numerator. So that's what this simplifies down to. I haven't taken any limits yet. I just did the algebra. Now I want to apply my ratio test. So this goes to what as n goes to infinity. Keep in mind that n is the variable here. X is a fixed but arbitrary real number. X might be 10 or might be negative 50, whatever it is, but n is the thing that's changing. For whatever fixed numerator I have, it's just a constant, this x squared. My denominator is getting larger and larger, right? The only n's that I have are in the denominator. This goes to 0. Regardless of the value of x. If x is 10 or a billion or negative a trillion, this still limits to 0. 0 is always less than 1, again, regardless of x. This always converges. So my ratio test says this converges absolutely for all x. Or in other words, I see that my radius of convergence is infinity, and my interval of convergence is minus infinity to infinity, or just the whole real line. When I have factorials in the bottom, which come up in quite a few important Taylor series and Maclaurin series, things converge very nicely. Things just pretty much converge on the whole real line. Let's look at this example. Sum n equals 1 to infinity of x minus 1 to the n over n. Again, find radius and interval of convergence. As usual, I will start out. I'll start out looking for what the ratio test can give me. An plus 1 over an. So this is x minus 1 to the n plus 1 over n plus 1. That's an plus 1. 1 over an is n over x minus 1 to the n. Or this gives me my x minus 1 bits turn into just absolute x minus 1 times n over n plus 1. Now again, what happens to this as n goes to infinity? The x minus 1 in absolute values, that nothing happens to that. But the n over n plus 1 goes to just 1. If you don't see that right away, you can divide top and bottom by n, and you get 1 over 1 plus 1 over n, and clearly the 1 over n goes to 0. And my ratio test says if absolute x minus 1 less than 1, we converge absolutely. If absolute x minus 1 bigger than 1, we diverge. And if absolute x minus 1 equals 1, it is inconclusive. So we converge absolutely on, well, when we are less than 1 unit away from the number 1, that's 0 to 2. We diverge on minus infinity to 0 open, union open 2 to infinity. And we have to check x equals 0 and x equals 2, the endpoints. We may or may not converge at either one of these. There's no way to tell from the ratio test. But again, we just check those two numbers now. So for x equals 0, I end up with some negative 1 to the n over n. And for x equals 2, I end up with some of 1 to the n over n, positive 1 to the n over n. You can see that it's quite often the case that we end up with an alternating series. So the alternating series test might have seemed like a very strange one-off test, but it actually does come in handy quite a bit here. This is the alternating harmonic series. This converges conditionally if we are concerned about that. And well, sum 1 to the n over n, that's just sum of 1 over n. That's the standard harmonic series, which diverges. So we do converge at 0, but we diverge at 2. Our radius of convergence we find here. Our interval of convergence, well, let me not write that yet. It's 0 to 2. We do converge at 0. We do not converge at 2. So I better have a half open interval, closed at 0, open at 2 for my interval of convergence. I get most of the way there from the ratio test, but I do need to check those two endpoints individually. We do converge at 0, not at 2. So that's our interval of convergence, close 0 to open 2. All right, I think I'm going to skip over this one. It's kind of cool because it's a series solution to a differential equation. Bessel's equation or one of Bessel's equations. But it's just a lot of algebra to work through. So, but we do see the n factorials on the bottom here. It turns out this is going to converge on the whole real line. So a nice solution to this second order differential equation that we see is more complicated than the ones that we've dealt with because it has these non-constant coefficients, which make it quite tough to work with. But this infinite series does converge on the whole real line. Let's look at this one in our last couple minutes here. Consider the series sum n equals 1 to infinity of n factorial times x to the n. As usual, find radius and interval of convergence. Let's again set up our ratio test, an plus 1 over an in absolute values. That's n plus 1 factorial, x to the n plus 1 over n factorial, x to the n. I see my factorials divide out pretty nicely. I'm just left with n plus 1 on top. And then my x powers divide out nicely, just leaving me with absolute value of x. I have n plus 1 times absolute value of x. Again, remember, x is fixed but arbitrary. It's some real number like 3 or negative 1,000, whatever it is, but it's fixed. The ratio test is asking what happens as n goes to infinity. Actually, as n goes to infinity, regardless of what x is, this goes to infinity. If I take whatever non-negative number for x, or yeah, one caveat, but almost regardless of what x is, this goes to infinity because of the multiplication by n plus 1. There's one minor caveat. What's the only time that this does not go to infinity? It's whenever x equals 0 precisely. It goes to 0 unless x equals 0, in which case it goes to 0. So we converge at x equals 0, and we diverge on minus infinity to 0, union 0 to infinity. We converge only at the center of the series. If x is non-zero, absolute x is strictly positive, and then we diverge to plus infinity in the limit. the ratio test says that because this limit goes to infinity, the ratio test says our series diverges. But if x equals 0, then if I look at n plus 1 times x, when n is, say, 1, 2 times 0 is 0. Or when n is 100, 101 times 0 is 0. Our sequence is just 0, 0, 0, 0, 0 forever. And when x equals 0, this limits to 0 and does converge. So what's my radius of convergence? It's 0, because there's 0 width of the interval where I converge. And what's my interval of convergence? It is the single number. Oh, so the single, I said single number, and I thought 1. The single number, 0, 1 element in there. I suppose you could write it as closed, the closed interval from 0 to 0, like that. That's probably kind of a funny way to write it. Probably better to just write it as the singleton 0, just the single number, the set containing just the number 0. And my radius of convergence is 0 because there's 0 width to this interval. Okay, and then let's look at one last example. I think we have 2 more minutes, we can get this done. I'll go a little quickly through this, but it's the same setup as before. We start with the ratio test. Oh, lost my +1 there. My x's divide out, leave me with just an absolute x. And then my 3 to the n divides out, 3 to the n plus 1, leave me with 3 on the bottom. And then n over n plus 1. I could rearrange this, I guess, a little bit. I can make this absolute x over 3 times n over n plus 1. This n bit goes to 1. And all the stuff that is left over after the n bit is taken care of when the limit is just absolute x over 3. And my ratio test says, when is this less than 1? That's when we converge absolutely. When it's bigger than 1, we diverge. Equal to 1, we're not sure. When is absolute x over 3 less than 1? That's when absolute x is less than 3. So I have a radius of convergence of 3. So I converge on -3 to 3. I diverge on -infinity to -3, open, union, open 3 to infinity. And I'm not sure what happens at -3 or at +3. I would check both of those cases. I can rewrite this as 1 over n times x over 3 all to the n. And when x equals 3, I get sum of 3 over 3 to the n is 1, 1 over n. Harmonic series diverges. And when x is -3, I get -1 to the n over n. Alternating harmonic series converges. So my radius of convergence is 3, and my interval of convergence, I diverge at 3, but I converge at -3. Close -3 to open 3. That's my interval of convergence. Okay, so this was the lecture where we kicked off the idea of power series. Let me stop the recording here.